lesson, we're going to take a look at tangent planes and normal lines. So this is building upon Calculus 1. So instead of having a tangent line, we're going to have a tangent plane, and we'll have a normal line to a surface. So that's going to be relative to a surface. So we can represent the surface in space primarily by an equation with z equals a function with independent variables x and y. In the development to follow, we're going to notice it's going to be much more convenient if we set this equal to 0 as a function of x, y, and z. For any surface, I can convert to this form as taking that function of x and y and just subtracting z so that I have everything on one side of the equation, similar to algebra. So because my function of x and y minus z equals 0, I can consider S to be the level of the surface that f is given by. So here's an example. I have a function, f of x, y, and z. So when I subtract a z over, I've got that z squared. And it's going to describe something given by the functions of x, y, and z equals 0. So the solution is, I can write this as x squared plus y squared plus z squared equals 4. Why do I want to write it this way? Well, if we think back to algebra, x squared plus y squared equals 1 is a circle. So if I have x squared plus y squared plus z squared, that's going to be a sphere, and the square root of what's on the right-hand side will be the radius. So normal lines are important. We know this from previous calculus classes because normal lines are going to help us describe the curvature, and they help us in multivariable calculus by analyzing the surface in solids. For example, if I think about two billiard balls interacting with one another, these are three-dimensional objects in multivariable calculus. When I strike a static ball, there is a line of impact that ball has traveled upon to act upon the stationary object with the amount of force. So if you think of this as force vectors, that may help make some connections for you. The impact can occur one of two ways. If the cue ball is moving along the ideal line of impact, then it's going to transfer its momentum to the stationary object. But if it's not really a great trajectory, it's going to stay stationary. So those are generally the two outcomes. If the cue ball is not moving on that line of impact, that specific trajectory, and it gets deflected to one side or the other, meaning it doesn't strike the ball, then it's going to keep part of its momentum because it hasn't struck anything to transfer that force to. That part of the momentum that's transferred when this occurs properly occurs on that line of impact regardless of the direction of the cue ball. Looking at this figure. So I can hit that line of impact multiple different angles. The line of impact will be called the normal line because ideally if I hit it at that, it's easier to say 90 degrees in Cartesian, but we want to hit at the origin of the XYZ plane, then I'm going to have the largest impact imparted. So in the process that we go through to finding a normal line to a surface, we're also able to identify the tangent plane. It's kind of like a really cool extra piece. So let's say I have some surface given by all of my variables equal to 0. And I'm going to let there be a point on that surface that's x naught, y naught, and z naught. I'm going to describe that using vectors. So I have the vector of x, the vector of y, and the vector of j. So for all of that, I need those to be 0 in order for me to have the equation. If it's differentiable at each component, and it exists at each component, I can then use the chain rule by differentiating with respect to x, keeping y and z as constants, then multiplying by the derivative of x of t. This is what we learned in the previous lesson. Plus, take the derivative of y, but x and z are constants, times the derivative of y of t. Then take the derivative with respect to z, so that x and y are constants, and I'm multiplying by the derivative of z. So that gives me that equivalent vector form. So we're basically taking what we did previously and building upon it. So the result tells us that this gradient at point P, so locate point P on my surface, is orthogonal. Now remember, orthogonal in the 2D plane just means perpendicular to. So it's orthogonal to the tangent vector of every curve on S throughout P. So that all the tangent lines lie in a plane, so within this plane, that are going to be normal again, but they're also going to contain that point. So think about it kind of like point slope. When I'm working with point slope, all the lines that go through that are parallel still go through that specific point. So the definitions of a tangent plane and a normal line are just conceptual changes from 2D into 3D, and this is going to be the equation of a tangent plane. If you look at the equation of a tangent plane, it is remarkably similar to point slope. So I'm going to have my point, and I'm going to take my x minus the x value in my point times that derivative that I'm taking there. Derivative of y with y minus the y coordinate, derivative of z with z minus the z coordinate. So it's kind of like having that mx minus x naught, because we know derivatives are related to slopes. So here's another example. If I want to find the equation of the tangent plane to the equation that I have given at a specific point, I'm going to start by making sure that I have it set equal to 0, because it's not a circle. So the reason I did not set the previous one equal to 0 is because I just had x squared, y squared, and z squared. Once I do that, I'm going to consider the derivative. So if I take the derivative of this function and I keep z and y a constant, that gives me negative 4x. If I take the derivative of y and I keep z and x a constant, that gives me negative 4y. And then the same is true for the derivative of z squared, which is 2z. I've differentiated everybody. At that specific point, I then plug in the coordinates to those points, and I get numbers out. So if I replace in this equation the x value, negative 4x, with 1, I get negative 4. If I replace the y value of negative 4y with negative 1, that's where these numbers are coming from. Then I'm going to plug into that point slope description. So I'm going to have my value times x minus the x coordinate. Notice the x coordinate is 1, so it's x minus 1. Then I'm going to have my partial derivative of y for my slope, y minus the y coordinate. Well, the y coordinate is negative 1, which means it's really y plus 1. And then I last have the coordinate of 8, so there's nothing to plug in, so it's just 8, but z minus the z coordinate, which is 4. Once I do this, I'm going to distribute, combine my like terms, and then I'm going to wind up with the equation of the tangent plane. So really, this whole process depends on your understanding of the chain rule and those partial derivatives. As just an additional note, this is the formula for a tangent plane. So I would just have you copy it down. I just added the slide in as a reiteration slide in case you didn't copy it down in the previous video.